Gresham College presents Measures Beyond Money, Part 2, Energy and Emergy, Measuring Well-Being Among Nations, by Denis White, Oregon State University.
Thank you, Michael, for the introduction, and I'm pleased to be here in London to talk with you about a measure beyond money. I'm going to start with talking a little bit about just the concept of value initially, and then talk about energy as one way to think about a different source of value than the ones that we've used so far. And I'll go on to talk a little bit about some applications of that, and then about how we've used that to look at sustainability at the level of national countries, of countries of the world. So there are many different kinds of value, and I just want to distinguish here two different concepts, one of which is I could call the donor-based value, which is value that's contained inherently in something based on some physical measurement, and that could be either things or processes or services or even information. And contrast that with receiver-based value, which is based on what normally we would say what humans actually consider something to be of value, in the sense ultimately that they're willing to pay for it in our economic system. So here's a very trivial, simple economic model where consumers spend money on purchases, and where producers spend money to buy labor from wages. And of course, these are exchanges. That is, the purchases are made for goods or for services, and those have some value associated with them. In our economy, they're associated with the monetary value. And similarly, workers get wages for their labor, which the producers are considered to have value for their purposes. But there's other sources of value that we should be recognizing. For example, the environment supplies us all kinds of value, much of which we don't actually pay for. And it could be energy sources, of which we do pay various ways for, but we don't pay the environment for them. We pay the people that produce the energy. And there's all kinds of other goods and services that the environment provides us as well, not many of which we don't have a way to appropriately value. So I want to just introduce the idea of thinking about it a little differently in terms of some of the principles of energy. So the first idea is that energy is basically contained in everything. It's contained not only in solid objects, but it's contained in processes that take place. It's contained in services that people do for other people, and so on. So there's always a transfer of energy, and in many cases a storage of energy that's around. So we can think about this in terms of available energy, and for any particular good or service, there is a certain amount of energy that was used to produce that good or that service. And that, I'll talk about how that can actually be measured as a potential source of value. One of the other ideas is that different kinds of energy have different value, and I'll talk a little bit more about that in a minute. So Emergy is the concept. Michael introduced it a bit with that originated with scientist Howard Odum in the United States back in the 1950s, and developed over really the latter part of the 20th century, and then has been continuing in the 21st century. And it's defined here as the amount of available energy of one kind that previously was used both directly and indirectly to make another form of energy or a service or a product. And we can think of it as energy memory. Another way of thinking about it that has been used in the past is thinking about it in terms of the embodied energy that's contained in a service or a product. In the Emergy research community, most of the studies that have been done, and there's quite a large number of those that I'll just mention as a side, that on the ZN website for this conference, Michael has posted reference to a website that has a large number of publications in this field. So if you're interested in those, I can talk about you later or refer you to the ZN website. In any case, most studies start with an initial source of energy and then express things in terms of that initial source of energy. And it's solar energy that's typically used because that, in fact, is the source of many, not everything, because we have internal heat source in our Earth that is also a source of energy. But solar energy is relatively convenient to use and has been pretty widely used in this field. And the units then are called in this field solar M-joules, Emergy joules. So Emergy comes from Odom's initial work in thermodynamics and physics and has been developed then by this research community over the years. There are a set of principles. I'll talk about a couple of those. And the basic idea is that we can measure any type of information or good or service in terms of the common units of these, in this case, solar M-joules, energy units of one kind or another. So energy quality is one of these principles that this group has developed and offers as an interesting idea to think about in terms of thinking of energy. And the basic idea is that calories of one form of energy are not necessarily equal to the calories of another form of energy in terms of the ability to do work. And so that quality comes from concentration processes, from the flexibility of the energy type, from the ease of transportation, and from how convertible it is. And so we can say that, for example, 1 joule of sunlight is not necessarily the same as 1 joule of wind power, 1 joule of fossil fuel, or 1 joule of electricity in terms of its ability to do work. So a related principle is the hierarchy of energy transformations, and that actually shows both the energy quality and the sort of hierarchical process. So here we have a diagram that is sort of illustrating how human labor results from sunlight through a series of energy transformations. So the sun gives the plants energy to create organic matter, which then is used through geological processes to produce fossil fuels. The fossil fuels are then mined and used to create electricity. The electricity is then used along with other fuels, of course, to create provisions for human use, such as food and clothing. And eventually, human labor can be produced as a result of the energy that's fed through this entire chain. And this particular diagram shows how, and these are measurements that I think have been made. I'm not quite sure who the particular reference is here, but this one suggests that it takes 20 million joules of sunlight to produce 1 joule of human labor. So here's a case where the concentration and all of the possibilities of increasing the quality of energy through this whole chain end up with the very valuable labor that we as humans do. So one of the aspects of those transformations is that, first of all, we can quantify the amount of energy, as the previous diagram was illustrating, and we can look at the ratio of the Emergy that entered into the system, which in that case of the previous diagram would have been 20 million solar Emergy joules, and we can take the ratio of that amount of solar Emergy and divide it by the actual energy, the available energy that's available as you come out of each step of that system, and we can use those then as factors to multiply energy transformations by. So those factors are called transformities. And here's a list of some typical ones. And some of these, for example, the human services one is one that showed up in the previous one. If we look, in that case, it was 20 million divided by 1. In this case, we're saying it's 100. On average, human services are worth 100 million solar Emergy joules, and so forth. So there's a whole series of of studies that have been done to produce these sets of numbers. And the other aspect of these numbers is that they're not single numbers. So it depends on the typical process. For example, there are very many processes that produce fossil fuels. Each process will have a different ratio of the amount of energy that comes out versus the amount of solar energy that goes into it. So these do vary depending on the type of system and the state of knowledge as well, because there's this as you may get a sense here, this is a fairly complex process to determine the energetics involved in various things. So there have been a number of Emergy applications, and I'm just going to illustrate two here. First, on the top, this shows another energy chain, and this is in the cells of plants, and it starts again with sunlight and goes into the chloroplast and then through several of the other constituents in the cells and ends up, in this case, at DNA. And there's a set of numbers that correspond to the number of joules that are going through each step here of the process. And then on quite a different application is looking at the agriculture in India, including their reverence for cattle, and showing how that system can be diagrammed here with the flows of Emergy between the different components, starting with the rain and the sun, which feed the rice crop and produce weeds, and then the rice is stored up, and eventually both cows and humans use the rice, and some insects are involved in it, and so forth. So it's obviously a simplified diagram, as most of these are, but it's a way to capture some of the essential components of this particular system. So the next two slides sort of try to get at some of the basic issues in using a physical basis for Emergy, for values such as energy, versus the sort of willingness to pay economics that we typically use. So first of all, if we think about scarcity, supply, and so forth, when we can say that when environmental resources are abundant, we don't need to take that much, it doesn't take that much work to obtain these resources, and therefore the costs are small and the prices are correspondingly low. And then the net contributions to the economy are the greatest then, because they are providing us with so much abundance. And because they are abundant, the standard of living is correspondingly high. On the other hand, when resources are scarce, the costs are higher and the supply is lower, and therefore the prices are correspondingly higher. So in those situations, real wealth, that is the real wealth that we obtain from nature, is scarce, and the standard of living is low. Now, of course, this is a simplified sort of description of this process. I mean, there's lots of other things going on, but in one sense, in terms of the sort of supply and demand view of things, this is one way to think about it. So, from that perspective, market prices are actually inverse to the real wealth that the environment provides. And we, as I mentioned earlier, part of that is because we don't pay the environment, in a sense, for the work that the environment does. We certainly don't pay in terms of pricing. I mean, we have various ways of trying to restore the environment based on the damage that we've done, but we don't even address very much of that. But in the cases that we do, it's either through regulation or through incentives for stream restoration or something like that. So we do have processes for trying to restore to the environment some of the value that we've taken from it. So The damage that we do, though, we should actually, in terms of a traditional accounting system applied to energy, we should be recording that as liabilities. And so here's a balance sheet. These are data that come from a study of the state of West Virginia in the U.S. that was done about 8 years ago. And this is an extraction. It's only a small part of the total Emergy budget that was prepared. So in this case, two of the important natural resources are the forests and the coal reserves in that state. But we also show here that the knowledge of people is important, and we have a valuation of that. And I can talk more about how that's been done to date. It's an active area of research in Emergy community. And then we have buildings as another asset. For liabilities, we have an estimate of the extraction damage from the coal mining industry, and then there are some debts on the building material of the building process. So for public and private equity, we have in this case 3 of the 4 that Michael mentioned. We have built capital. Well, that would be physical capital. I guess that would correspond to natural capital and human capital. And the built capital in this simple balance sheet is simply the buildings, the energy of the buildings minus that for the depreciation and for the debts, the bonds that are outstanding. The natural capital is the sum of the forest and the coal energy minus the extraction damage for the coal mining. And the human capital is simply the knowledge of the people that are listed here. And so in the balance sheet, the idea is that they balance out. So in fact, here they do, based on the arithmetic is fairly trivial here. So, but the illustration is that you can actually make an Emergy budget in the same way that you would do a traditional accounting budget using a monetary value. So another sort of application is with international trade, and here is where Emergy can reveal some of the imbalances in trade where otherwise we would consider the trades to be fair. And so this is based on a study from about 20 years ago in Ecuador, where they were replacing mangrove forests and swamps with shrimp farms. And so if we think about the exchange that was going on here, where the United States was buying the shrimp and Ecuador was then buying goods and services from the United States, and if we assume that the monetary exchange actually, that all of the money that Ecuador received for shrimp was funneled right back to the U.S. to buy clothing or whatever they would be buying from the U.S., then we can look at the difference in the Emergy flows that were corresponding to those equal dollar flows. And in this case, Ecuador came out on the short end by a factor of about 4 because the process of producing the shrimp yielded, and the shrimp, the value, the Emergy value inherent in the shrimp that were shipped to the United States was worth about 4 times more than the goods and services that they received for that same amount of money. So finally, I'm going to look at how we've used the Emergy concept to think about sustainability. And it starts with a fairly simple diagram. And I think I'll switch to that and talk about it and here. So it's a simple matrix here. It's 3 rows and 2 columns. The 2 upper rows and the 2 columns, the 4 red box symbols indicate the Emergy flows, the proportion of Emergy flows in the 4 categories. So we have local renewable, local non-renewable, imported renewable, and imported non-renewable. And those numbers all add up. They're percentages of the total, so they add up to 100. And then we also have the 2 blue boxes, which show the proportion of exports, which were renewable or non-renewable, and those add up to 100 also. So we've done these analyses for 163 different countries, and this is the averages across all of those 163. So They're fairly evenly distributed here in three of the four boxes: the local renewable and non-renewable, and the imported non-renewable. And the imported renewable, not too surprisingly, is relatively low because most people that are using renewable resources use them locally or fairly locally. They don't typically export their wood or their sunlight or whatever. So that's why that number tends to be typically lower. So here are three countries that are kind of at the extremes of the patterns that we see in these in these Emergy budgets as depicted this way. So Ethiopia is pretty highly dominated by its local renewable resources. Algeria by its local non-renewable resources, and Belarus by imported non-renewables. And so those are sort of three of the three countries that represent sort of a characteristic. Should I take questions now, Michael? Do you keep going? Okay. I guess we'll have there'll be some time later for. Yeah. For 8 of the countries in Western Europe and the United States, the patterns look like this. Some of them they tend to be more similar to Belarus than to those other two extremes, in the sense that many of our countries are fairly dependent on imported fossil fuels, and those tend to show up. But Spain and Portugal, somewhat interestingly, are more dependent on their local non-renewables. And then of these 9 countries, Ireland has the highest local renewable proportion in its Emergy budget. So how do we get to sustainability from this? Well, it's fairly simple. We define sustainability as the sum of renewable local and renewable imported Emergy. So it's based on the proportion of renewable as a percentage of as a part of the entire budget. And then we also talk about we have a similar sort of index, the self-sufficiency index, which is simply the sum of the local renewables and non-renewables. And so for the average of the 163 countries, the sustainability index is 39% sustainable, and the local is 67%. And so then this is what that pattern looks like across the globe. And not too surprisingly, the countries that are low on sustainability tend to be the US and Mexico, Central and Eastern Europe, Spain and Portugal, North Africa, and part of the Middle East, parts of the Middle East. And the highest sustainability, the 3 countries adjacent to Venezuela and South America, some countries in West and Eastern Africa, Mozambique and Madagascar, and several countries in Southeast Asia. And self-sufficiency, there are many more countries that are in the 80 to 100% category of self-sufficiency than of sustainability, and so we see all of South America, quite a bit of Africa, a lot of Asia, less of Europe, and less of North America. And so here are just some tables of the top 10 in most sustainable, least sustainable, most self-sufficient, and least self-sufficient. In the case of the most sustainable, most self-sufficient, most of the countries are African. And in the case of least sustainable, many of them are oil producers or high consumers of fossil fuels. And the least self-sufficient, I think 6 of those are European, and then there's Lebanon and Israel and Taiwan and Sri Lanka make up that list. And the percentages there. Under most self-sufficient, those numbers are quite high, and not surprisingly, based on the map, we know that many countries are 80 to 100% self-sufficient. So the other part of this that we've started working on is to compare this with some of the other fairly common indices that look at some aspect of human welfare or environmental activities. And so we've compared with the Human Development Index, the Happy Planet Index, the Environmental Performance Index, and the ecological footprint. The Emergy data that I'm been showing here today for these countries is based on the year 2000, roughly. I mean, not every statistic is for the year 2000, but that's the year that we've tried to standardize the data for. And so we chose so some of these, for example, the HDI, the UNEP produces those for multiple years. We used that for the year 2000, and likewise with the other indices. Happy Planet, I'm not sure if they were in the business before 2005, but someone here may know the answer to that. I'm not sure. What is surprising about the comparison is that none of these things correlate, or no pair of these things has a very high correlation. The only one that is above 0.5 is the positive correlation between HDI and the footprint, the Human Development Index and the footprint, and that's 0.7. And with the two indexes that we've developed, the sustainability and self-sufficiency, we all have negative correlations with these other indices. So there's some interesting issues here in terms of how are we measuring things, and are there some other ways to be thinking about doing things. So I'm going to finish then with just with 4 points. First, I want to assert again that real wealth is the value in human goods and services, but also in non-human environmental goods and services. So that's, I think, an important point. Gets back to the donor value concept that I mentioned at the beginning. And thinking about energy as a possible way of looking at real wealth, one of the positive advantages of it is that it is, in fact, very omnipresent in our world. And third, energy has this idea of having different qualities in terms of where it stands in a chain of transformations of energy from some source, say sunlight, to some kind of output. And finally, I'll argue that as we understand it now, Emergy appears to be the most comprehensive and scientifically correct method for valuation. And I just want to make one other point. A colleague of mine in the Emergy community has argued for the fact that if, in fact, there were an Emergy-based valuation system and a currency was built that was based on that, on Emergy value, that, in fact, all of the market processes and everything could work perfectly assuming you had perfect information. There wouldn't be any conflict necessarily between a monetary system and a physically based energy system. I mean, the markets could function this as well, hopefully even much better than they do now. So I'll end up with that.
For all information, please visit www.gresham.ac.uk.